Hello everybody! We are going to finish up our section with geometric probability distributions. So first we need to define what a geometric setting is. So it's in a binomial setting, but there are sometimes special ones that fit this geometric type pattern. If you've seen geometric sequences, this should look fairly similar, but we're going to proceed as if you haven't seen those. So with our binomial variables, we're looking to count the number of successes. But in a geometric setting, we're looking for the goal being to repeat a chance behavior until we get a success. So we're going to do it over and over and over until what we want happens. And we're going to look at the probabilities associated with that. So here's the official definition, and just like with a binomial probability setting, there are four conditions. We had bins before, and now we have bits. It needs to be binary. There has to be success or failure. The trials must be independent, and this time, instead of the number of trials being fixed, we need to have a goal to count the number of trials until the first success occurs. And the probability of success must remain the same from one trial to the next. So again, that's bits. Sort of like the bins for binomial, but bits because of the number of trials that we are going to do. So we have this geometric distribution, and we're going to look at what that looks like. It's the same sort of notation, but we're looking at the number of trials y. So our random variable is y, and that is representing how many trials we need to do until we have a success. So the smallest value of y that we could have is 1. That should make sense. And it could go on and on and on forever. And the only parameter that we have is the probability of a success. So one thing you do have to pay attention to is that just like with binomial random variables, it's important to make sure that you can use a geometric distribution. If it's not geometric, we can't use what we're about to go through. So we're going to look at an activity. So here it is. It's the birthday game. So your teacher plans to give you 10 problems for homework. Take a minute and read this problem, and then let's talk about it real quick. So pause the video. Alright, so if one person guesses right, we have one homework problem. If the first person gets it wrong and the second person guesses right, there's 2 homework questions. If 5 people guess wrong and the 6th guess correct, there's 6 problems of homework. Otherwise, we can just have straight 10 without playing this game. So the question is, are you ready? Does it make sense to play this game? So we're going to verify first that y, the number of guesses, is a geometric random variable. So we look at bits. It is binomial. A success would be a correct guess. A failure would be an incorrect one. The trials are independent. Each child guessing is independent of the next. We're switching to different friends of the teacher. T, we're counting the number of guesses up to and including the first guess. So our trials are being counted. And S, the probability of a success, the probability of guessing correctly is constant. It's 1/7. We have a 1/7 chance of guessing the right day. So I want to find the probability that we get it right on the first one, second one, third one, and on the kth one. And it should make sense. The probability that the first student guesses right is 1/7. For the probability of y equals 2, that means the first student got it wrong and the second student got it right. So make a guess as to what you think is going to show up here next. And I hope you thought it's going to be 6/7 times 1/7, which is 0.1224. Failure first, then success. Y equals 3. Make it a guess what you think is going to show up here. We're having the first 2 students guess wrong and the last student guess correct. There's our probability. Do you notice a pattern? I hope that you do. If y has a geometric distribution with probability of p success, the probability of y equaling 1, 2, 3 up to k, if k is one of these values, is 1 minus p, probability of failure, to the k minus 1 times p to the first. Notice these exponents, they add up to whatever k is. So failures to that number times the probability of a success on the last one. Notice there is no binomial coefficient in front here. We don't have to worry about that because it is going to occur in this order. A bunch of failures, then a success. If we look at a graph and a table, this is what we see. This is what we see for our distribution. We have our probability table right here. It does go on forever. We can't show the entire distribution. It could take 500 guesses before somebody guesses right. Is that very likely? No. But could it happen? Yes. So let's talk about a description of this. The shape, it's heavily right skewed. The most likely value is getting it correct on a 1, first guess, and that probability is 0.143. That's the most likely. The center, the mean is 7. We could calculate this out or approximate it. And what that means is we're expecting it would take 7 guesses to get our first success. We're expecting 7 problems of homework. The spread, we can calculate the standard deviation. Our standard deviation is 6.48. So 6.48, we're expecting that the number of homework problems the students receive would differ from 7 by an average of 6.48. So we could get 1 homework problem or up to 13 homework problems. That would be a reasonable expectation for that. On average, that's how much the data will vary. We're calculating the mean and the standard deviation the way that we did with binomial probability. And if y is one of these special geometric random variables with the probability of p successes, then its mean will always be 1 over p. 1 over the probability of success. And that's a little bit different than n times p, like we saw with the binomial. Slightly different formula, but we get a mean of 7, 1 over the probability of a success. So, a summary of section 6.3. You can pause to make sure that these bullet points look familiar to you, that nothing looks strange and startling. And in the next chapter, here's what you'll be yet to see.